Let's learn the table lookup principle next. Relatively speaking, there are many basic concepts of routing. So we must first lay a good foundation. I've drawn a reference picture for you now. I now make a connection to the line. Certainly. I drew this picture for the convenience of the lecture. If you are planning a project in the future, such planning is a failure. But the lecture, this is a very typical case. For example, it is 192.168.1.0, 24-bit mask. This is a network segment behind this device. This is a 25-bit mask. This is a 30-bit mask. I teach you how to draw. Draw a line here. Add an arrow here. This means that there is a network segment behind the device. Okay. This is 3 network segments. You will find their 192.168.1.0 place is coincident. Let's say this is device 1. This is device 2. Device 3. And device 4 below. We plan the next hop for them. Suppose here is 1.1.1.1. 30-bit mask. Its peer is 1.1.1.2. Suppose here is 2.1.1.1. Its peer is 2.1.1.2. Further down this is 3. 1.1.1. Its peer is 3.1.1.2. They are all interconnected. This is the interconnection address between them. Now no matter how. In short, now I have learned the following routes. Whether static or dynamic. Now this one-by-one route. Learned all the equipment. Then these 3 routes will be added to the table. There is a routing table on the device. 192.168.1.0. 24-bit mask. Add all 3. Because the identification must be a different destination network segment. So it must be added, regardless of how the rear equipment is connected. But what is happening now is that all tables are added. So now comes a data. This data will go to 192.168.1.2 in the future. So where is the next jump? Think about it. Now comes a data. The destination address of device 1 has been reached. 192.168.1.2. There are now 3 options for the device. Here, here, and here. So where will it be sent from? When the device receives such a route, how to judge which line it should go to? Now there are so many. Which one should be matched? First the local will calculate. When we talked about ARP before, we said that take your own mask and add the IP of the peer. Match with yourself. Router 2. Now the data is going to 192.168.1.2. It will take out all the local matches and calculate them. Look. 24 can match it. The calculation is the 1.0 network segment. Both 25 and 30 are calculated with it. Whoever counts. Calculated and found that this network segment. It means that the data is now going to this destination. All can match. Then the longest mask will now be chosen. That is, we'll select a mask of 30 bits. Since the mask is the longest, represents a longer network bit. Host less. Then the purpose of visiting in the future. Although it is a destination network segment, but in the end it is still a precise destination IP address. The fewer IP addresses covered in a network segment, it means that the network segment is more accurate. For a 24-bit mask, there are 254 usable addresses inside. That is, if it matches the network segment behind the device, it has 254 addresses to match it. But if now go to this 30-bit mask, it only has 2 precise addresses in it. So, If all three can match now, we will choose the one that believes the mask is the longest, because it will be more precise. If this 24-bit mask is matched, it may end up going through a few more routers to arrive. So the path we choose is one step. Choose the most accurate. This is a lookup principle. Then there is a difference between the table lookup principle and the table addition principle. The lookup table principle is called the longest mask match. That is, if there are multiple matching routes locally, it will be forwarded according to the longest mask. Suppose. Now comes a new data. Go to 192.168.1.4. Then it should go to device 3. That is, go to the 25-bit mask here. Then if 1 comes now, 192.168.1.130. The next hop should go to device 2. Because now the maximum of 25 bits can only reach 127. Here are some differences between them. So for now in the routing table, there is a more magical route, called 0.0.0.0. The mask is also 0.0.0.0. Route like this. Let's call it the default route, also known as default route. Let me explain the default route. Draw a simple picture. This is an export router of your company. This is the operator. I won't draw the switch. This is a PC from your company. The router will then access any internet data. Find its gateway, because it must cross the network segment. Find gateways across network segments. The data arrives at the gateway here. Its destination IP now relies on a DNS. The destination IP must be resolved locally. Then it will be sent to the router. For example, data is now going to 2.3.4.5. Such an address. Let's say this is Google's address. Now this device. If you want to help forward, this device must have an address to 2.3.4.5. Assume that a large amount of data will be accessed every day in the future. All such addresses. This terminal has to send data to the public network every day to access services that vary from company to company. Then please, is it necessary for every route of this export device? There are about 800,000 routes on the entire public network. Do you want to go to every address on the public network? Do we need more than 800,000 routes? This device cannot bear such a large routing appearance. If the future comes a data, look up data from the routing table. Match the previous route. Then forward it. That theoretically, I go to the public network. As long as I do the business of the operator, we all take the carrier's equipment. Can go anywhere. Export this device. If there are more than 800,000 routes now, send a piece of data. When searching the routing table internally, more than 800,000 routes retrieved one corresponding forwarded out. From sending data to Google to receiving its reply, maybe 7 or 8 hours have passed. The data has not been sent yet. Secondly, the routing table itself cannot bear such a large appearance. Who will configure it including this appearance? Does the engineer need to manually enter one by one? It's out of the question. If you want to run a dynamic routing protocol with the operator's equipment, first will not run. Second, even if it actually runs, do you need to rely on dynamic routing protocols to pass 800,000 routes to each other? This is too exaggerated. So we have a simple way. Since I now want to access any business on the public internet, all walk operators, then I will write a route now. This route represents all routes. That is, represents all addresses on the public network. Even all addresses in the world that conform to the IPv4 address configuration format. Write all. No matter where the data goes in the future. Take this device for the next hop. For example, this is an interface for interconnection between operators and devices. You will also assign addresses in the future. As long as you run services with fixed bandwidth, there will be a fixed address to connect with you. There is a static. We'll point to the operator on this device. As for how it got back, don't worry. Now for business. There is a route for the egress device, called the default route. Represent any piece of data in the future. Can match these 40. 4 zeros represent unknown. Represents the least precise, because its mask is 0. The longest mask match means it is more accurate. The longer the mask, the more accurate. Its mask is 0. Then it must be the least accurate. Some students may think that 800,000 routes are not too many for routers. Although it is a network device, the hardware used must be more advanced than PC. But we collectively call it a piece of hardware. Its computing power is also limited. If between devices, even if the data is sent out, query locally. How can more than 800,000 routes reach this device? Words learned through dynamic routing. Does running a protocol interact with each other so much? Then the overall bandwidth does not need to do other things. Just interact with the routing table. Business data cannot be forwarded at all. Suppose now there is a route 123.1.2.3. For example, next hop right is null. If there is a data coming now, can it be matched? Originally, if there is no this route to come here, just drop the packet. A data came. Device 1 helps it forward. Check the routing table and found no. This data is discarded, because the device can't help it forward. Now a route comes in on this device. Is the default route. Now if we match. Can it match? OK. Is allowed. For corporate exports here. Write a default point to the operator. Go to any business on the public network in the future. As long as the data reaches the gateway, it receives this data to help forward. They all go to the default operator. Same. Send this 123.1.2.3. It is possible to match. Only here because I didn't draw another line. Write next hop. I can only write a none to it. This thing you will learn in the future NP stage. I now ask you another question. Now comes a route 192.168.1.3. If send now, who will this traffic be sent to? OK. Will be sent to device 3. Because the following does not cover this address. So will 1.3 match this default route? Look at the data now. It also matches 4 zeros. It does not limit each bit. It seems different from others. Will not match the default route. The concept of default routing is, if there is now a route, at this point its destination and mask are both 0. In this situation, it represents a default route, also known as default route. So if it's a route like this, it can match all IP addresses in the whole network. But why doesn't it match what we just said? For the default route, since its mask is 0, it is a route with the worst matching order. Only when there is no local route to match will match the default route. Now comes a data. Check locally first. When it is determined that there is no precise route in the routing table, we'll match it to the default route. But unfortunately, there is a route here. Can help with precise forwarding. Then this default route will not be considered. Only as we just said, such a network segment sent over will consider the default route, because there is no detailed route locally to reach it. So the default route will be considered. Here are some relations between them. The above is about the addition and lookup of routing tables. We make a summary. For routing, if you choose to add routing table now, multiple routes now want to appear in the routing table. Then to make a comparison, to confirm the final route can appear in the routing table. This is called the principle of addition, followed by table lookup. If the current data arrived at a router, the function of the router is to help forward data. There are now multiple lines can go to the destination network. Then at this time, the local will be based on the routing table that has been generated. Select the one with the longest mask and send it. If now can't match any exact route, then if there is a default route locally, just match the default route and send it out. For example, now there is a default next hop. Point to this device. Just give it the traffic. There is a route to 1.1.1.1. Put the traffic to the middle, instead of going down. Here are some of the principles we talked about. Finally, let's look at the lookup table. Longest mask match. For example, I can now write 4 static routes. There are 4 S. Stands for static. Can point them to the same next pick. In theory, as long as the principle of addition table is met, it can be added. It doesn't matter if the next hop is the same, as long as the mask is inconsistent. Different purpose network. Different network segment. So now no matter the next hop is inconsistent. Add all. The routing table we are talking about now. It is referenced to the destination network. As long as the following mask is inconsistent. Different destination network. Go to the only destination network. There will be a unique route. It will be processed by adding table principle. In addition, what is the difference between the default route and whether it is null? This may be misleading everyone. Logically speaking, we can add another line here. Add a device here. Let's say it's 4.1.1.2. 30-bit mask. It is also in the same network segment as it. This will write the next hop to here. Just because I didn't draw this device, I can't write a next hop. So I can only write a simplest way. The next hop can be represented by null. It's like I dropped it into a black hole. Black hole routing. But the NA stage will not learn this. The default route also points to the next hop. If the future comes a data arrives here. These 3 routes do not match. Data go here. Match the words. It is equivalent to such a route. Next hop is here. Then the null I just wrote is also the next hop. Only, the representative is not to send out this route. Instead, the route is discarded here. Let's review next. Whole router forwards packets. When the data is forwarded as a whole, each router, actually, the parameters in the second layer are to be modified. Then why do you want to modify? When we learn the routing table of the complete body, everyone should understand. Because every time RA performs routing table lookup, local will see what is the outgoing interface on the device now. Now after this route is forwarded, this data is sent to the next device. For example, now the data arrives at the device. Then before arriving, when sent from the previous device, the next hop address is the address of the left interface of the router. The device forwards this data, sent to RB. So now the destination IP address. It is the address of the left interface of RB. When we do data encapsulation, if the third layer is the address of this interface, and both of them are a directly connected network segment, from RA to RB, When it is making an ARP request. To request the MAC address of RB. That is, when this data is sent. The destination MAC is the MAC of this interface. The next time you retweet, destination MAC is its MAC. Further down the target MAC is its MAC. This is the purpose MAC. Let's look at the source MAC. When future data is forwarded as a whole, the source MAC will be the MAC of the outgoing interface. For the current data, each forwarding through a layer 3 router, separated by the interface of the router. On each different link, both the source MAC and the destination MAC will be changed. The router must know the next hop outgoing interface to send the data. Therefore, when the router forwards data, it will have some corresponding problems. The source MAC and destination MAC will be repackaged. This parameter will be changed. We will use the MAC of the outgoing interface as the source MAC. And the address of the next hop is used as the destination MAC. This is a concept between them. That is, data arrives at the router. Disassemble the second layer. Then look at the destination IP of the third layer. And then proceed to retweet. Forwarding process. The source port and destination port of layer 4 are unchanged. The source IP and destination IP of the third layer are unchanged. The source MAC and destination MAC of the second layer are always changing. Okay. Next, we will start to officially enter the part of static routing. What we just said are some basic concepts of routing. Static routing refers to manual configuration and maintenance by administrators. For example, now there is a routing device in the company. All routing entries inside. In addition to direct connection, I typed them one by one. For an enterprise network. In fact, only static routing is enough for small enterprise network. Also used by large enterprise networks. But it is not used as the main, because it will be more troublesome. As for the reason, we are in the process of experimenting. Can come to discuss. Let's first look at. This is the current terminal. Usually, the gateway is generally configured on a layer 3 switch. If I now send traffic to the gateway to export equipment, then export the equipment to the operator. This is a process of flow. We are often in the early stages of learning. The easiest thing to overlook. Traffic now goes to the gateway. No problem. Direct connection between gateway and egress device. No problem. In the future, we will write a static route pointing to the operator. No problem. The data can be exported as a whole. But what we tend to overlook the most is the how did this data come back? The operator now needs to reply data packet to these devices on the internet. For example, now the left is a network segment of 1.0. On the right is a 2.0 network segment. Then when the final data comes back, corresponding to return to 1.0 and 2.0. Otherwise the data will not come back. This is when using static routing. A more tedious part. You have to specify. This drawing is relatively simple. Let's discuss a slightly more complicated scenario. I draw it casually. Normal drawing is not like this. Real networking. It's not going to be grouped like this. Let's say this is some router. Simply make a connection. We are not discussing structural issues today. Assuming the current topology. That's how it's connected. For example, this device now has a network segment. More than one segment. There may be very many subnets. 1.0, 2.0, 3.0 etc. And I also want to subnet it. ABC that is not the main class is used. We also have a lot of subnetting. Then there could be hundreds of subnets. There are so many network segments on the left side of this router. The rightmost router is assumed to be 6. This is 1. For example, a PC is connected here to access the following network segments. If you want to access the network segment of 1.0, then we have to write the root in the middle. The characteristics of static routing are to write one by one. For example, if you want to go to the 1.0 network segment from here, then write a. Not only this device needs to write. The equipment that passes along the way should also be written. For example, the current route is like this. Then the 2 devices. There must also be hundreds of subnets behind. Then each has to be configured individually. Some students may ask, can it be glued after it is configured? Can't. Because the next hop is different on this device. For example, the next hop is the interface address. On this device say, the next hop is this interface. On this device is this interface. So there is also no possibility of bulk copying. Of course we can modify the next hop in the TXT document. Can but don't have to. Go to 1.0 like this. Go to 2.0 like this. Go to 3.0 like this. This is what we say. You need to configure manually. This is a characteristic of static routing. Then you have to write hundreds of articles. All the devices in the middle have to write these hundreds of entries. So compared to, it is more cumbersome. And now it's just traffic. Finally the data has to be returned. This device only knows how to go to 1.0 now. But it doesn't know how to get to the PC. So in the end this traffic have to keep pointing back. All the equipment along the way. Two-way routing must have. Otherwise, the traffic will not pass. Let's take ping as an example. Data goes back and forth. Then when the data comes back, there must be a route. So the limitation of static routing is that if there are more devices in the future, when there are many network segments, it's a little hard. It doesn't fit well. Because every node has to write. Over workload. And more error-prone. Not easy to troubleshoot. Because it is written statically. If you look at it, you have to look at it one by one. Dynamic routing protocols are different. If some problems arise in the middle. For example, add a network segment. Delete network segment. It can synchronize itself. As long as the dynamic routing protocol is running correctly. Then it won't have any problem. But the first routing configuration we learned. Definitely a static route. Let's start with how to configure static routes. This is a command. Everyone can remember. Show run. Include IP route. That is routing that is currently running on the device. It is the route I configured for it. There are 3 ways to write routing configuration. This is the router for RA. For example, from here to start a writing. Which network segment to go to in the future? Which address should the next hop go to? That's one way. We don't need to look at the picture above. Just look at this configuration. It means I have now written a static route called IP route. Then the destination network segment is 192.168.1.0. The mask of the destination network segment is 3,255 and 10. That is a 24-bit mask. But it's not allowed to make a bar 24 here. Spaces are also not allowed 24. Must be 3,255 and 10. Then specify an outgoing interface. That is, go to the 1.0 network segment now. Specify an outgoing interface is 10. The second configuration. Destination segment. The mask of the destination network segment. Plus the IP address of the next hop. Third way. Destination segment. The mask of the destination network segment. Plus the outgoing interface. Add the IP address of the next hop. Okay. What is the difference between them? First, the top one is not recommended. I would never recommend that you write like this. Because under the current Ethernet, it will have some problems. What is the specific problem? Let's talk about it in detail later. The second method is the one we use the most. When you go to configure in the future, use the second. No other. The third is the most comprehensive. Can but don't have to. Not necessary for most cases. If in the future you will learn scenarios that must be specified as such, you just go to study alone. It has very few application scenarios. Now most of the configuration will focus on the second. This is the most common way now. Let's first discuss. Why don't you suggest that you write an interface? Let's look at this picture. I told you before. If we look at the topology in the future, this one line connects 3 devices. Indicates that this is a switched network. It's like a switch is connected in the middle. This is a switched network. It means that they are all on the same network segment now. This is a relationship between them. Now 3 device interfaces. In the same network segment. So now we have a problem. If now RA. If you want to go to 192.168.1.1. If it is an outbound interface, then there will be corresponding problems now. Data can come out of this interface. This is no problem. But after the data came out, whether to go left or right, this we have to consider. Because there is no provision for the next hop. So what exactly is this data going to arrive at? Our RB interface. Or our RC interface. Don't know. So it creates problems. That is, if only the outgoing interface is specified. Under the current network, multiple devices can be connected through a switch. Let's say it's a switch in the middle. Then they can all be in one network segment. Now I want to forward a data to device 4. For example, data arrives at a network segment. Is behind it. That for us. Only the outgoing interface is specified. Traffic is sent from here. But I don't know where the next jump will go. So in general, will not specify the outgoing interface. Like in this picture. If you want to visit 1.1 now. Look. If I want to visit 1.1 now. Go left. If bad luck, only one outgoing interface is thrown out. If you go to the right, the traffic will be blocked. So it creates problems. Since it creates problems, then why is this outgoing interface? Will it appear in our PPT? This is also a problem. Let's look at the line in the middle. When we talked about the transmission medium before, I told everyone, this cable is called a serial cable. The link it identifies. Point-to-point link. It is an interface of one device connected to an interface of another device. There will never be any other equipment in the middle. Like we just said. A route. A switch. Connect multiple routers. Actually they are called logical interconnections. They both use switches. Can connect to each other. But for point-to-point links, it is not possible to use equipment, such as switches in the middle. Point-to-point link. As long as the outbound interface is specified, it means that the final traffic must reach the peer end. After the data is out, can't get anywhere else. Only to the peer device. So as long as there is a route to the peer, to send the data. Then under this link, serial line 2 interfaces. It is possible not to configure the same network segment. That is, on the left is 1.1.1.1. On the right is 2.2.2.2. As long as there is routing, direct communication between them. That for the current Ethernet. Both ends must be configured with the same network segment. If you do not match the same network segment, will create some problems. This involves a data encapsulation problem. I'll just tell you. The device on the right does not need to encapsulate the destination MAC, because for a point-to-point link, the device on the left can directly find the device on the right through the address. So no need to get the MAC on the right. And what we're talking about? Networking based on switches. Such Ethernet. That is, LAN networking mode. The left device must find the MAC of the right device. Because there can be multiple devices in a LAN. Then need to be on a link. Locate which is this device. So you need to send an ARP request MAC. The point-to-point link does not need to send ARP. Here's the difference between them. Let's move on. Let's take a look at the configuration of static routing. We're about to get into the experimental part. The experiment I assigned to you is the one in the lower right corner. You can do all the experiments in class by yourself after class. We turn the device on. Start up. I use both devices. Want to do a little experiment? I'll take a screenshot of it now. Put it in the picture and say it. Now here are two devices. For the right end, I configure it with a loopback address. Can simulate a network segment behind. Plan the address. 192.168.1.1. On the right this is 192.168.1.2. I want to simulate now. A network segment is connected behind R2. It is the network segment of 1.1.1.0. There is a way. I can connect another router here. Configure 1.1.1.1 for this interface. Configure 1.1.1.2 for the peer. This means that R2 now has two interfaces. One interface is 1.1.1.1. One interface is 192.168.1.2. Then it is equivalent to available from R1 here. Access to the 1.1.1.0 network segment of the backend, which is equivalent to I want to simulate now. There is a network segment behind, whether it's a PC or a device. In short, a new network segment has been added here. I hope that the simulation can reach this network segment. It is equivalent to adding a new network segment, but it is relatively cumbersome. When going to configure, I want to pull an extra device. Power on the device. Name it. Configure it with an interface address. Then configure an address for its interface. Represents that there is now a network segment. This way is troublesome. So when we experiment, would not choose this method. The way we choose is open a loopback interface on this device. Configure an address for the loopback interface. That means there is a corresponding network segment behind this device. Then we don't need to pull another device. No need to configure an internet address for it. This means that the rear of the device is now equivalent to a router's virtual interface. Configure an IP for this virtual interface. Then this interface has an advantage. Just never down. This interface will not be down, because the interface will be damaged. But the virtual interface will not be damaged. There is such an interface on this device. Then often for routers, the address of this interface. We can also use telnet to this device. Debug it. But this interface, not for experiments. We will learn many configurations in the future. The relevant configuration inside will use the loopback interface. But at the CCNA stage, if we choose the loopback interface, just use it to simulate a network segment. We can do it in two ways. One is the loopback interface on the device. One is the interconnection interface. There will be some difference between the two. But usually, the loopback interface is not used much. This is the content of NP. That is, it's not just for experimentation. Right now such an experimental phenomenon was simulated.